Hi all, and welcome to the Emergent Vision Technologies Anatomy of Volumetric Capture Systems presentation. I am John Eilert, founder, president, and CTO. I look to give an inside look at how our many customers utilize our products to create their systems. Our customer applications range from 8 cameras up to 250 cameras within a single system. There are many considerations in selecting the appropriate technologies, and we leverage the knowledge acquired over the last 10 plus years in the propositions we present. A short introduction and outline for the presentation is in order. We'll start with a brief description of volumetric capture, what it is and what it is not. We will follow this with descriptions and considerations in the selection of the components within such a system, such as cameras, servers, switches, cabling, lighting, and the rig, a structure to mount cameras and lighting. We will follow this with a video demo showing how ECapture Pro software creates and manages a system from the ground up and manages the whole workflow of a recording session. We will then look at a few examples of systems ranging from as few as 4 cameras to as many as 250 cameras. This will illustrate the scalability of such systems. Lastly, we will look at the typical architecture of such a system and consider advanced architectures in this space. So what is volumetric capture? Volumetric capture is a technique used for creating precise 3D models using multiple synchronized cameras. These models are then integrated for playback for a variety of applications using tools such as Unity and Unreal engines. An early variation of such work was in the creation of the bullet dodging scene in the Matrix film. Images were captured from around the subject at roughly the same time, and then in playback the viewer rotated around the subject. Such techniques are now heavily in use in entertainment and sports applications. We've all seen marker-based 3D model capture, which is suitable for some applications where low-cost and low-quality 3D models are acceptable. You can think of volumetric capture as markerless capture, where a virtually infinite number of invisible markers are used to capture the highest quality 3D models. Here, the camera's sensor pixels are assigned to points within the scene, and more pixels generally means more invisible markers for higher quality capture. Technically speaking, 360 video is not volumetric capture, as for this content creation, one may use a camera as shown in the bottom right, where the cameras are inside looking outward. Volumetric capture is more so where cameras are outside looking in. Although experts in the areas are utilizing volumetric capture data to create content for a 360 video from an arbitrary point within the volumetric capture space. Here consider that a goggle-equipped viewer could be placed anywhere on a football field and see everything in 360 from the perspective of that single point. At a high level, a volumetric capture system is comprised of cameras, servers, switches, cabling, lighting, and a sturdy rig for mounting the many cameras, light fixtures, and cabling. Servers, switches, and power sources sit outside the rig, often in a server room. For anyone wishing to set up a typical system, the software development is the most challenging and time-consuming part of such an integration. In addition to being a primary supplier of cameras for such applications, we at Emergent Vision Technologies also provide our ECapture Pro software for near turnkey integration. The combination of cameras, software, consultation, and support have made Emergent a must-stop shop for many companies from startups to Tier 1 corporations over the past 10 years. So how does one go about selecting a camera for the volumetric capture camera array? Resolution for typical systems is in the area of 12 megapixel to 25 megapixel, but we've seen also as high as 65 megapixel or even 100 megapixel. This decision is based upon the spatial accuracy required and thus number of invisible markers as mentioned previously. Frame rate for typical systems range from 30 frames per second at 100 megapixels to 100 frames per second at 12 megapixels. The choice of frame rate is based upon the temporal or time accuracy required. Faster moving subjects naturally need higher temporal accuracy and thus higher frame rates. Cable length can be a major factor in choosing a camera technology. The largest indoor rigs can be as much as 50 meters in diameter. Even with smaller rigs, cable runs back to the server rooms or trucks for portable setups can be in the hundreds of meters. Certainly, cable runs around stadiums can be in excess of 1 kilometer. Even the wiring around the rig can be heavy and cumbersome with thicker cabling. It is for this reason that the majority of customers within this space prefer fiber cabling, which is interfaced directly to all components within the system. Many installations are also pre-wired with fiber to further solidify as medium of choice. Image quality is a huge factor, and emergent cameras integrate the best-in-class image sensors from the likes of Sony and G-Pixel. Consider the impact of a camera-based fan in the application. Noise from the fan is disruptive for audio recordings within the volumetric capture space. A fan is also a sign of higher power consumption, so consider that within recordings, if a fan is turned off during the recording, that the camera will heat up possibly to the point of overheating, but at least to the point of creating a noisier image. This is one point that can limit recording times in some systems. Consider the design of the rig itself and the placement within the rig. More compact and lightweight cameras are better overall. Cameras can be placed closer together as needed, and the rig can accommodate more cameras, and structural requirements can be reduced. Consider that getting the images off the cameras in real time, so a faster interface is needed. Such an interface should follow strong cross-industry standardization, as provided by the IEEE with the primary Ethernet interface and protocol. Consider what lens interface you will need. The most common interfaces in this space are C-mount, F-mount, and EF-mount for iris and focus software-based control. All of these points are addressed in the design of Emergent's multi-platinum award-winning cameras. The servers are responsible for 4 important aspects of these systems. They provide the interface to the cameras for control and image capture. They place the captured images into a storage solution such as SSDs and RAID arrays. All of this is managed within Emergent's ECapture Pro software for near turnkey deployment with no software development required. The choice of server specifications factor into the maximum number of cameras a given server can accommodate. The most critical specifications are memory and storage performance. We at Emergent can provide consultation on such server requirements, but consider that a typical performance server can support anywhere from 12 to 24 cameras running at 12 megapixel with 60 frames per second. It is worth discussing here the limitations associated with using cameras with built-in storage, such as M2 drives. A common storage capacity is 1.92 terabytes. The maximum recording time possible with a lower-end recording is about 30 minutes for 12 megapixels with 60 frames per second. For 65 megapixel with 60 frames per second, this would provide only 5 minutes maximum recording time. Some of the best new sensors in the market are the Sony Generation 4 back-illuminated sensors with resolution of 25 megapixel and frame rates of 100 frames per second. For example, the IMX 530. For this sensor, such a recording solution would only support a bit over 8 minutes. Consider then, after the recording, that one must wait to retrieve all the images from the camera's storage to allow playback on the host computer, which can take as long as the recording itself, and much longer for large camera arrays. This would prohibit live streaming, which is being currently done by pioneers in this field with the introduction of 5G technologies. A reminder that these same cameras would also have fans, be less compact, and be less lightweight. As we move to higher resolution cameras and/or higher frame rate cameras, this approach is not sustainable and even less friendly to the overall workflow for volumetric capture studios. We suggest to avoid such technology to achieve instant playback, top performance, be most scalable, be future-proof, and support live real-time streaming. Switches are standard components within IT infrastructures worldwide. In medium to larger volumetric capture studios, these switches perform three primary tasks: communication between all system components, like servers and cameras; camera multiplexing, which allows many cameras to be reduced to single connections back at the server for reduced PCI Express slot count and thus reduced server cost; PTP synchronization also, which allows all cameras to be exposing at the same time. We at Emergent can provide consultation on such switch requirements, as well as help in switch setup for your installation. All volumetric capture systems require cabling. Aside from power cabling, the cables are primarily for high-speed communication. The most common choice is fiber for its simplicity to work with, especially when pre-existing fiber runs are present within an installation. At each end of a fiber are low-cost fiber transceivers, which slot right into the cameras, switchers, and server NICs. Power cabling is often distributed around a rig for cameras and lighting. Some may have heard of PoE, or Power over Ethernet, which can simplify cabling for lower speed cameras. But a 10 gigabit Ethernet and higher is either not practical or simply non-existent, since the big players have switched over to all fiber technologies such as SFP+, SFP28, QSFP28, etc. For those who must bundle fiber and power cabling, then options such as hybrid cables are readily available, but generally localized power is the most foolproof when dealing with lossy DC power distribution. At its core, the rig is simply a structure for mounting cameras, lighting, and cabling. We have worked with customers on systems supporting up to as many as 250 cameras per system. The rig sizes involved range from 2 meters to 50 meters in diameter and had anywhere from tens to hundreds of lights. Our friends at Esper specialize in such rigs, and as one can imagine, if this is not designed properly, that subject lighting can suffer, or even worse, that the whole rig crumples down due to poor structural design. That said, many find more simplified designs which work for their applications. Consider that some systems are simply one level of cameras, which allow for simply right and left rotation around a subject. It is more common to have multiple levels of cameras, or even cameras all around a given sphere, to capture varying levels of tilt. Since the dawn of the camera, scene lighting has been a critical factor in achieving the best photographic results. This was for 2D imagery. Imagine now having to create optimal lighting for 3D capture. In the end, you get what you put into it, but consider that once the recording session is done with your famous client, that if any detail is missing due to poor lighting, you cannot fully recover this. Two primary approaches exist. Uniform lighting is the most common and is suitable for most applications. Where the finest of details are desired, multispectral approaches are employed. Our friends at Esper specialize in rig and lighting design, and they can take the guesswork out of this aspect of volumetric capture system deployment. That said, many find more simplified designs which work for their application, such as simple uniform panel lighting. Shortly, we will take you through a simple workflow for setting up the system utilizing emergent ECapture Pro software. Once the software is installed, the following steps are followed to generate the images, which are then provided to post-production 3D reconstruction workflows. We will start by configuring the system, which means defining our capture servers and assigning cameras to server interfaces and providing storage locations for the camera images. We will then make some adjustments to the cameras for a desirable image, such as exposure, gamma correction, focus, etc. We will then create a project to manage the scenes and takes for a given session. We will then do a recording. Lastly, we will play back the recording in both temporal or time mode, as well as spatial or 360 mode. Here we go with the ECapture Pro Demo. We start by specifying the capture server. We next configure the network interfaces on that server that we will use for camera control and video streaming, and the software goes out and finds all the cameras on those interfaces. The next step is adding the drives that will be used for image storage. We then assign drives to groups of cameras based on camera bandwidth and drive performance. Lastly, we apply the system configuration which completes this task, and cameras can all now be accessed for control and video recording. We now adjust and configure the cameras in preparation for a recording. We start by creating groups of cameras in the system for easier management. We create a calibration group for one camera, a high-speed group for 4 cameras, and use the default group for the remaining cameras. We then assign the cameras to the desired groups. Let's detach the calibration camera window and perform a quick calibration. We will adjust exposure, white balance, and gamma factors for a more pleasing image. We can even use the false color feature to highlight where the image is overexposed, so we can deal with that by lowering the exposure. With all the camera settings optimized, we can zoom in on a calibration block to properly align the camera position. Using the focus tool, we can get a quick quantitative visual of the quality of the focus and adjust in real time to optimize. We can then propagate the camera settings to all other cameras if desired, and repeat the alignment and focus adjustments on those cameras. We can also save the camera settings to a file for reloading at a later time. Let's reload those settings now. And then take those settings and propagate them to all other cameras. We can also choose a camera settings file for loading all cameras at software startup. Let's take a look at project management. We'll start by creating and naming a project, scene, shot, and take. In addition to creating calibration takes, you can also create a background take for later comparison with the primary recording. Here we create a single frame background take for all cameras. We then review the details of this take within the Project Management tab. Now it's time to record. We switch over to continuous recording mode and then start the recording. While the recording is active, we can review the recording status for important parameters like drive space, synchronization, CPU usage, and temperature, and more. Color-coded indicators with user-defined thresholds are used for clear indications of problems if they exist. At the same time, all information is also logged for later review. We now wait for the recording to finish. We stop the recording. Lastly, we review the status of this recording to confirm there were no issues seen. In Playback, we will look at the recording of one camera on a time or temporal scale. At any time during this recording, We can pause playback, and at that single instant in time, cycle around all cameras in 360 mode for a full 360 view of the subject, which is a great new feature for highlighting this money shot to your important clients. In playback, we can also look at a scene in slow motion. We can then view a scene in reverse. And can also fast forward a given scene. We pause again and enter 360 mode for a review of another money shot. This concludes the ECapture Pro demo. Emergent has worked with customers on systems of a variety of scales. The smallest systems employ as few as 4 cameras, and these are typically hardware triggered for synchronization, which eliminates the need for the PTP aspect of the switch. Since no switch is present, we cannot multiplex the cameras, but instead we provide 2 dual-port NICs to interface to the 4 cameras. The server would also hold a storage solution suitable to the application. Only one installation of the emergent ECapture Pro software would be required. A typical medium-size application might have 12 to 24 cameras. For such a system, we recommend a switch to provide the PTP and multiplexing benefits discussed earlier. Such a system would have a single NIC card and single RAID controller in the server for a high-performance 2 PCI Express slot solution. Still, only one installation of the emergent ECapture Pro software would be required. A large system might have as many as 250 cameras. For such a system, multiple switches are used to provide PTP and multiplexing for the cameras back to the capture servers. Each capture server would have a single NIC card and a single RAID controller for local storage. The capture servers would be multiplexed back to a central control or navigation PC to provide a single user interface for full control of the whole system. In this case, installations of ECapture Pro software would be required on all servers in the system. A standard architecture and application is shown here. Images are captured and recorded in real time. 3D reconstruction is performed in post-production through either on-site or edge processing solutions, or through a cloud computing service such as Azure. The resulting 3D models are later used in playback integration via Unity or Unreal engines. An advanced architecture and application is shown here. Images are captured and recorded in real time. 3D reconstruction is also performed in real time through the use of on-site or edge processing solutions, coupled with a cloud computing service such as Azure. As one might expect, there are challenges associated with taking large amounts of image data and compressing and processing this down to create 3D models in real time. This is not generally appropriate for the best quality 3D models, but rather for live events, video conferencing, or other content where quality is not as crucial. This quality will naturally improve over time and will revolutionize the way we work and play. Thank you all for joining us for the Emergent Vision Technologies Anatomy of Volumetric Capture Systems presentation. Another thank you for those who asked questions during the presentation, and I hope we can follow up on any unfinished discussions afterwards. I am John Eilert, founder, president, and CTO, and I look forward to discussing the details of your applications. Feel free to contact us, and we look forward to hearing from you. Thank you.